morning, everybody. Nice to see you all. Most of us made it safely. Still like good weather. Wake up to a nice storm.
Woke up at 3:17.
Is that when your power went out?
Well, no, it got out like an hour before a tree limb fell on our roof.
Nice.
Yeah, it's fun.
We had a pretty big branch across the street. It was fun. Anyway, we're here, so we're going to whiteboard the data that you gathered yesterday. So in a little bit, I'm going to have you get with your partners. We would like both data sets on one graph. What other information do you think you should put on there?
Your schools.
Yeah, your school characteristics, the constants. What else? Definitely the EOL. We're good? All right, when you're all done, hang them up, and let's try and organize them in some fashion so that they're a little easier to pay attention to. All right, have at it. I have the boards here for you. Markers right over there.
Alright, John, where you at?
Oh, yeah. Okay.
I'm not sure if there's anything wrong.
Do you have a question?
Yeah, like our things, like one of our lines is the same as theirs, but then one of theirs. So one of us stuff.
There is, I think, another group that'll have the same.
Yeah, that was
school. I mean, not yet, guys, but similar schools will be able to see which one it matches. But just put down the ones that you.
Yeah.
But
Something went wrong.
Any questions for me?
I forgot to put those both in the same graph. I think there's slopes and stuff.
Yeah, you can do it, but Morgan, how about for you guys?
No.
You're good? Okay.
Did you get like what each school was, like number 30?
Yep.
Okay.
And then
Yeah, I agree.
You're good.
Yeah.
okay, so the bottom, this bottom one is the first one. Oh, this one is our first set.
Yeah.
So this one is
there is.
one is two. So then we're right.
120 centimeters.
Our EOL is for.
I can go back.
Okay.
First one.
At the first slope.
Austin, how about yours?
We're good to go. We finished
Gauge
yesterday.
30.
Okay.
And
3.08.
3.08 joules per coulomb.
And then our EOL.
Oh, what is it? This one.
And then
This one is 1.56 joules
Sounds good.
per coulomb. Per coulomb per second. Official notes.
Draw out the slope, the top one.
This is, oh, this is it. The yeah. Well,
Number
I don't think one. Alright, other one. The other one is.
Yeah. Some of our one is.
terrible.
Delta B, what was this? I.
We're taking the origin.
Yep.
Wait a minute, was the origin slid to the left or was it always in there?
It always is.
Mr. Hurdy? Yep. Do you want us to simplify the units if we can?
You can just put them down, what you came up with. They'll get some pile up.
If you want to rewrite it like that, you can. Bring it down.
Like we had 1.45.
Oh,
Guys, are we organizing that by like length or gauge or something?
what was this number?
Remember each group had like a partner set. Right, so these two were together, right?
Sorry. We started off as that.
And
Our partner said it.
Those two are next to each other.
these two are good.
So there you go.
We were partners.
So we,
Yeah.
not six.
Yeah, so all three of these are pretty close, right?
So there's six more.
Where is yours?
I'm gonna just put this one down on the other side so it's a nice layer.
Get some. Go out down.
Yeah, see, no, I think it's because I was thinking.
You were?
Yeah,
I think that's all of them, right? All right, now that we've got all the boards up there, let's do our full slab. It looks like it's pretty good data. So regardless of what the school characteristics were to start out with, when you look at all of the boards, what's the common theme across all of them? Say a little bit again.
Linear with no intercept.
They're linear with no intercept. We do have one board that was drawn with an intercept. Well, two intercepts.
Oh, that's just how it looked on the chart that we can send,
So no auto scale?
so. You can do it.
Or did you check with the 5% rule? So they're all linear and it looks like they have no intercept. We like it when they turn out to be linear, that's the easiest one. Let's put that one in conceptual terms. So for somebody that's not sure what exactly that graph is telling us, let's explain it for them. Yeah. As the current increases, the electrical potential difference also increases. Good. say that delta V is proportional to I, or the potential difference is proportional to the current. Why would it make sense then that there's no intercept? Everybody hear that? A little bit louder for us.
With no current, there should be no volts. Potential.
Yeah, or we can flip it around also. If there's no electrical potential difference, there's not going to be any current. We're okay with that? Good. What about if I were to double the electrical potential difference? What would that do to the current in the circuit? Double it. That's the easiest one to understand. Linear relationship. So we've dealt with the intercept, we've dealt with the relationship. Let's take a look at your slope. What's the most obvious thing about your slope right away? Well, it's a constant slope, good. Linear graph gives us a constant slope. What else? Hey, say a little bit louder for everybody.
Positive.
It's positive value and it's not a universal constant. How do you know it's not a universal constant?
That's guessing looking at the numbers of it.
With different characteristics, why it changes the slope.
Yeah, I mean, if it were a universal constant, then no matter what spool characteristics you had, you'd get the same slope no matter what. But we don't see that. So let's jot that down. So it's not a universal constant, but it is constant for a particular spool. What sort of observation can we make about the spool characteristics related to the slope?
The one in length is changed, so the one with greater length has higher slope.
Okay, so Landon is suggesting that the one with the greater length, greater slope. Were there other groups that saw that same thing? For the group, then let's take a look at it. We would have to make sure we use the same diameter. So these two have the same diameter, right? The longer wire definitely had the greater slope value. Same thing here. And there. It looks like it holds all the way through. Okay? Let me write that down first. So, longer wires at a greater slope. And we also talked about the gauge number, right? What did we notice there?
The smaller the gauge, the greater the slope.
And when we had a smaller gauge number, was that a thicker or a thinner wire?
Smaller gauge is thicker.
Smaller gauge is thicker, and the slope value was. Are we sure about that?
Oh, isn't it gauge number, as the gauge number is bigger than?
As the
slope
gauge number
bigger?
is bigger, that's a thicker wire,
Okay.
which had a
Greater.
Smaller slope.
smaller slope. Is that what our data shows?
That's what we got.
We have to check these last four boards over here. So here's the same length, same material, This group is suggesting with the spool that was a 30 gauge, which would be thinner, had a smaller slope value. Well, no, I take it back. The number's bigger, they just have them labeled differently. That's a bigger number there. How about over here? This is their smaller one. It had a bigger slope. Spool 1 is that one, right? And that relates to this one, so it was smaller. Over here, A was the higher gauge number, and it had a higher slope. So everybody's okay with that? Higher gauge number means it's a thinner wire, and it has a greater slope. Yes. All right. And I'm going to just sketch another graph so that we can use that as our discussion. We are going to label one of those long and one of those short, which would be the long one. Which would be a thicker wire.
Smaller one.
Blue one? Okay, let's see if we can't narrow in on what exactly the slope means. Let's take a look at the units. You know, it's the units that really tell us what it is. We start out with a volt over an amp. Did anybody use those, or did we go right to the ones that were hidden inside each of those? Hidden inside, okay. And a volt we said was a joule per coulomb, and an amp was a coulomb per second. Did we simplify, or attempt to simplify?
Seconds over Coulomb squared.
Say one more time, Ryan.
Joules times seconds over Coulomb squared.
Did anybody even dare going inside a joule? You tried, Tommy? Does it work? It doesn't make it any simpler. Doesn't make it anything we necessarily recognize, right? Right. So when we try and simplify it, and it doesn't go to simplify to something we recognize, what does that tell us? Yeah, it's something new for us. All right. Let's build a conceptual definition of it. On the top we have, let's go to this one. We have the electrical potential difference, right? And I'm going to add that that's what would be required for, that's the top part. What would be the denominator? The electrical potential difference required for what? Well, not just that current, but an amp. Yeah. So when you take another look at your boards, we'll just go to the center board. For 160 centimeter wire with 30 gauge nickel chromium, this group is suggesting that it takes 25.64 volts to have a current of 1 ampere. Same spool, this group said 23.2, so that's pretty close. That's pretty close. But if you notice when you compare the two spools together, there's different values. So to get the 1 amp of current, let's just make the assumption that this is 1 amp. For one of my spools, I only needed that value, but for the other spool, a much greater value. So it would almost seem like for that second spool, right, for the longer or thinner one, because it takes more energy to get that same current, that same rate of charge flow, that there's something opposing the motion of the charges. Conceptually, does that sit okay with you? You could also see it if you tried the other direction. Right? If you pick a particular potential with a particular potential, one of them has a greater current. It goes the same way. So the slope conceptually is the energy required for a current of 1 amp. And when we compare two of them together, it's like there's something opposing the flow of that charge. Because not all spools would give us the same electrical potential difference for an amp. What might we call that? I think some of you are a little familiar with it. Yeah, that's how we would define electrical resistance. What symbol do you think we represent resistance with? Capital R. So resistance is represented with a capital R. The units are, just like we talked about, volt over an amp, which would be a joule dot second over Coulomb squared. Just like all of the electrical quantities we've done so far, it's given its own special name. That's called an ohm. So electrical resistance is the slope of our potential difference versus current graph. Conceptually, it tells us how much that particular material resists the flow of current. We're okay with that? We represent it with an R. It has units of ohms. And ohm, the unit ohm actually has its own symbol too. The reason, the reason would be, if I write this, without a doubt you know I'm talking about a potential difference. If I write this, you know I'm talking about current. But if I were to write this, well, you're not sure if that's 250 and I forgot the units, or it's 25 and I forgot the units, or if I really meant to say 25 volts. That's why it's got its own. When you take a look at the boards again, we have slightly different values for each spool that the groups did. How do you think we could determine which is the right number, or what the actual resistance of that spool is? Hook up a multimeter. We haven't used a multimeter yet. But it's very concrete. Multimeter, many meters. We've got a meter to measure voltage, voltmeter. We've got a meter to measure current, an ammeter. It would make sense that we have a meter to measure resistance also. It's called an ohm meter. But it really doesn't come as its own separate meter. It comes packaged together in a multimeter, and the ones that we have are actually digital multimeters. They are sitting right over there. So what I'm going to have you do, the spools are still over here. I'm going to have you you and your partner grab a multimeter, grab your spool, and then we're going to practice learning how to use that multimeter to measure the resistance of your spool. And then you can switch and get your other spool too. You can then do a percent difference along with your analysis. We're good? All right, so grab your spool, grab your multimeter, and then I'll give you a hand showing you how to use it. Yours is all yellow.
Look at the ammeter.
All you need is your spool, folks. All you need is your
That's
spool.
the place in front of the numbers. Yeah, that had to be wired. Slope was like crazy.
Tim, all you need is your spool. Just your spool.
Yeah, you walk right. Yeah, it's not a problem.
If you've used one before, by all means, go ahead and give it a try. If not, I'll walk over in a little bit and help you out also. Let's do both of these groups together. Yep, and the way it works is, so this, it can measure potential difference. This would be like batteries, this would be like an outlet. The ohm symbol measures the resistance, that measures the current. So these are the different ranges that it can measure. That's up to 200, that's up to 2,000, up to 20,000, up to 200,000. Ours probably was not over 200. Well, you may have to replace your battery. Okay, well, let's give it a try. And then all you're going to do is take the leads and make a really good contact right on the posts. Yep. Yep. And sometimes if you just poke it right on the top, you have to make sure you get pretty good contact.
Electric. The recurrence. Actually, 24.4.
It's too big. So it's like 1.018.
So about 32. So record that as that. Okay. So this would be for our potential difference. It can be direct or alternating. This is for transistors. We're not going to worry about that. That's current. That's capacitance. We're not going to worry about that either. We're going to do resistance. The different settings are the maximum value will be. So up to 200, up to 2,000 times 10 to the third, or up to 20,000. So ours are only 200, less than 200. So simply,
Then you just touch both sides.
yeah. And you do have to kind of dig in a little bit and make sure you have a nice solid connection. Ready? You gotta work it. Yeah, sometimes if you go on the top here, increase it to just 3.9. You have to get a little bit better.
24.1 and it would be perfect.
And then it should settle down. 23.9.
You're close.
Yeah, we got it. How close were you?
Well, it was right on our slope.
I wanted to talk to
So that was 24.2.
Austin and Tommy?
Austin and Tommy, yeah.
No, yeah, I know where we missed the decimal place on the ammeter.
You did miss the decimal place.
19.2.
Yeah, so it went up to a maximum of 1.
Oh,
Yeah.
that didn't stop.
Okay.
We have 32 together.
Okay.
What we do?
So I just always put an out right here, so back here.
Do you guys still have your?
Oh, it's 41.
Oh, which gauge is this?
Or 0.2.
And that just tells us the maximum.
26.
So up to 200, up to 2,000, up to 20,000, 30,000. So we're definitely going to be no more than 200. And then I think it looks like you measured it pretty well. You do need to make it pretty good.
Yeah, we loved it there for a while. We didn't for it to calm down.
Did you switch?
Let's see, it's.
No.
Make sure you switch spools also. Measure both of the resistance of both of your spools, okay? There's one other feature about the digital multimeter that when you're done measuring the resistance I want to show you. So when you're all done, you measure both, call me over and I'll show you that other feature.
14.5. Or, it's really.
No, we didn't.
Okay, so this is also a Honda Series car as a symbol. So it can tell us if we have one sensor, but it looks like a little speaker. So
This is,
if we complete the circuit,
thousands, I guess, and thousands.
we should have gotten an AMC battery.
Yeah, you have to like shove that sensor to it.
We should have gotten a little sound. So, if, for example, we think this spool is broken. No, it's got a complete circuit. So sometimes when you do bulb boy, you say, oh, I think you're bringing up my light bulb. It's kind of a handy troubleshooter.
Remember on the thing they tried to get into this guy. Yeah, I don't know why you can't stop them.
I don't know. I'm not good at it.
You should put it in the top.
That's what I usually do.
Actual minus predicted divided by predicted. So this is 26.00. So it'll be 0.5. No, not this
One more bit.
We should probably get this math done on it.
If we're good on the first one, we should probably be good on the second one.
Were you close?
Well, we're supposed to try the actual like percentage.
That one was a little bit more off. We had 25 points before. Okay. You remember how to calculate the Yep.
Yes.
Yeah.
Well, I was just going to show you that it also can serve as a kind of cylinder.
Is there a one?
Yeah, it's the same school.
So this is the third one. Okay. Just touch the two of these together once. Yes, yours is your battery's a better one. But it should put out a little signal to tell you.
How did they get 14 to 1? We got 27. No, that's really not.
Well, the way the ohmmeter itself works is there's batteries in there, and it puts out and it measures the current. So the resistance is really the ratio between those two. And you're getting 30 for that, right?
Well, we were first, hold on.
This thing's on?
So this means it's just.
What it actually is.
This would be
Yours good?
the top value that you can enter on that, so up to 200, up to 2,000, up to 20,000, up to 20 million.
Okay.
I have not ever used the 20 million, but in the experiment we're gonna do a little bit. We'll use some of those.
Okay, so yeah.
What would be 20 million? Well, you've had the digital electronics class.
Oh, wait.
There are little devices that we can put into the circuit that have
For
fixed resistors. And really, that's what these do. We put resistors in the circuit to control the amount of
I
current.
guess you can have really big resistors.
3.08.
Yeah, well, it depends. Like, for example, let's say I only had 6-volt batteries. And the light bulbs we were using for bulb light, those only operated with a maximum of 3 volts. I could put a resistor in there to make sure that this got some of the electrical energy also, so that the bulb wouldn't burn out.
New minus old divided by
Our
old.
error is too small.
So new would be the actual,
So the actual minus,
Relatively close, yeah.
your theoretical
okay.
divided by
Negative
4
14.
theoretical.
No, it should be divided by actual.
There's 4 like everyone.
Pretty sure it's divided by actual.
For that one.
We were within 5% for both of ours. Yeah, like.
Yeah, so then your new.
Well, it's depending on how you're connecting it.
It should fluctuate a little bit and then settle into a number.
Okay, well there's 9.8.
I don't know.
Be a skilled
Yeah.
Try connecting it on those skirts.
Yeah.
And with this one, you're saying it measures 14.
Oh my gosh. That would be terrible.
It took me like 45 minutes to measure all of it.
Yeah. Oh, jeez. How many pieces did you have on the right
They should be pretty consistent. Well, resistors are sold based on the tolerance. So what would be an acceptable range? Keep your meters right there. Has everybody had a chance to do their percent difference? Hopefully we were within 5%.
Yep.
On average.
Okay. Let's finish this because there's 3 other things we should still talk about. Okay? So we now can write the general model for potential difference, current, and resistance. So delta V, Y equals, our slope was the resistance. Current was on the x-axis. That one should go in our toolbox. That's known as Ohm's law. The thing that's convenient or nice about Ohm's law is it applies not only to small individual elements within a circuit, like we did, the current through your spool and the potential difference across your spool, it works for entire circuits also, even ones that have more than one spool. We're okay with that? We'll use that quite a bit. If you think about what we did yesterday, I said you should wait a little bit to draw the circuit, the schematic for your circuit. Your spool, we really don't have a schematic symbol for spool, but we do have a schematic symbol for something that we put into a spool, or excuse me, into a circuit to control the amount of current. That's a resistor. So in your toolbox, also, schematic for a resistor looks like that. And that's really the symbol that we should use for the spool when we draw your schematics. What questions do you have for me so far? So if we step back a little bit, we can kind of draw a bigger relationship now because we know that there was a factor that related our length of our spool to our slope, which we now know is resistance. So how is resistance related to length? Yeah, greater the length, the greater resistance. We can write it like that. We can also realize that there's one for the gauge, which we said related to the cross-sectional area. So how does resistance relate to the cross-sectional area of the gauge? That's an inverse relationship. If we were to put those two together to make one relationship, what would it be?
R is proportional to L over A.
Well, we can try that. L over A. In one part of the experiment, we held the gauge or the cross-sectional area constant, right? That's like taking that out of the picture. I see my first relationship. Longer wires had more resistance. This set of groups over here held the length constant but changed the cross-sectional area. Take it out of the picture. Right? Okay. It would be nice though if we could have an equation for that, right? And, I should have mentioned this earlier, and there's one other variable that we haven't really talked about. What was that one? The material. Because we didn't have the ability to really change the type of spool and keep the length and the cross-sectional area the same. So, if we were to plot a graph so that we could turn this into an equation, what graph would we plot? A little louder for me.
Length over area.
Length over area. Would it be linear?
Yes.
Good. And the slope, that would be our constant, right? And in this case, what factor about the spool do you think it would relate to?
Material.
Right, that would be the material constant. We're not going to do that experiment. Those spools are set up to do it, but there's something else we're going to do with them that I want us to do. The material constant, whoops, is known as resistivity. I know, resistance, resistivity. It's represented with that symbol, Greek letter rho. And it is the material constant for resistance. So you get another glorious model that looks like this. Usually it's applied to a wire. We probably won't use that all that often. The resistivities are a lookup value, but,
Much like the,
I'm sorry, go ahead, Calvin.
much like the frictional constant.
Yeah, like the coefficient of friction. Although this does have units. What units would the resistivity have?
Meters over meter squared.
Well, we know that this has to come out in ohms, right? And over here we've got meters, and underneath we've got meters squared. So what has to be in here to give us just plain old ohms? I didn't hear it. Yeah, so resistivities are expressed in ohm dot meters. The reason I wanted you to see that model is because when we did the pre-lab discussion, we talked about all three of those factors. Material, length, and area. And that's really the relationship that puts all three of those together with resistance. Well, it's a lot so far, isn't it? And we're not done yet.